test on Monday? So exam 3 is Monday, the 25th. And the topics are up through rigid bodies, number 10. So the things I'm going to start talking about today, it's still rigid body stuff, but you don't have to worry about that. That's, well, we'll get into that. Does anybody have any homework questions or any questions related to the test? Number 9. Is that what I said? Number 9?
No, I just have a question.
Oh, okay. My first assumption is I said something that contradicted something else I said.
You need it.
Oh, yeah. Okay, so neglect gravity. So this thing is hovering in space, or you can think of it as a plate moving on like an air hockey table or a sheet of ice or something. The rectangle shown has a length of 2.1 and a width of 1.3. So this length is 2.1, this is 1.3. The density is 2,500. So density is 2,500 kilograms per meters cubed. That's rho. So rho, because we have finite letters in the universe, rho has to stand for a few things, but density is one of them that it always stands for. The thickness into the page is 0.1 meters. And this angle, 40 degrees from the vertical. So actually, this isn't drawn quite right, but this angle is 40 degrees. That might be 40 degrees. And at this point, there's a force vector of negative 200, negative 150. So I could write that as 200 newtons that way and 150 newtons that way. And at this point, there's a force vector of negative 400, positive 300. So 400 newtons this way, 300 newtons this way. And at the instant shown, omega is negative 6 radians per second. This is a planar motion, so that's about z. And the velocity of the center of mass, so if we call this point, well, call that COM. So the velocity vector of the center of mass is 5, -3 meters per second. We're neglecting gravity, so the only forces are these two. This thing doesn't have a fixed point anywhere, and we're trying to calculate these things. Velocity at A, so this is the point A. This is the point C, and then this is the point B. So those three vertices. We want to calculate the velocity vector at A, the velocity at C, and the acceleration at B. Okay, so for us to do part C, if there was an angular acceleration or an acceleration of the center of mass, we'd have to know that. So we can assume that that's 0 and the acceleration of the center of mass is 0. And all right, so for the velocities, this is kind of a conceptual thing, although if you went through the calculation, you could go the long way through the calculation, and then when you started plugging stuff in, you just realized that those forces didn't have any effect on the velocities. But forces affect accelerations, right? Forces affect the translational acceleration of the center of mass, and moments produced by forces affect the angular acceleration. Okay, forces do not instantaneously affect the velocity. You can think of the velocity as the result of all the forces that object's experienced up through time up until that instant. Velocity you can think of as related to an integral of forces. Okay, so these forces that are applied at A and C don't have any effect on the velocity. Okay, the only things that have an effect on the velocity are the angular velocity and the velocity of the center of mass, and then we're going to do the calculations based on that. Anybody have any questions about that, what I'm getting at there? Okay, so anytime you have forces drawn and you're asked for a velocity, you know that those two things are independent of each other. As an aside, velocities can affect forces in some cases. If you have like viscous friction, air resistance, for example. Well, I guess those are sort of two separate things, but yeah, if you have friction that depends on viscosity, that friction force depends on the velocity of the object. If you have air resistance, the friction air resistance force depends on velocity, but it doesn't go the other direction. Okay, so velocity at A. Well, the velocity at A relative to the ground, and if it doesn't tell you specifically what you're calculating velocity relative to, then you have to assume it's the ground, is equal to the velocity at A relative to the center of mass plus the velocity of the center of mass relative to the ground. This one's given. And this one's circular motion. So this one is going to depend on omega cross r. omega is 0, 0, -6. That was given. And now the r vector, generally, what does the r vector, what's the definition of that r vector? From the center of the circular or spherical motion to the point that you care about. In this case, we're using this to calculate the velocity relative to the center of mass. And that means that everything is rotating about the center of mass for this calculation. Okay, we're assuming the center of mass is the fixed point. And so the r vector for us goes from the center of mass to that point A. Okay. Let's do this, because laziness is a great motivator of clever ideas. Let's call this our x-axis and this our y-axis. Okay, our z-axis is still coming straight out of the page. And now it's pretty easy to calculate that r vector. You don't have to use cosines and sines and trigonometry to figure it out. So we're going to go in the negative, from the center of mass, we're going to go in the negative x direction, 0.65. And then we're going to go in the positive y direction, 1.05. Negative 0.65, positive 1.05, 0 for z. And so the velocity of A relative to the center of mass is 0, 0, -6, crossed with negative 0.65, 1.05, 0. Can someone calculate that? 6.3 and positive 3.9. And then 0 for z because it's a planar motion. That's meters per second. And now, what if we wanted to represent that? Like, what if we were asked in this problem to represent that in like a normal looking coordinate system? So this coordinate system is this. And actually, if you think about, so we're being given, okay, so it's probably safe to assume that we're given force vectors and velocity vectors in a coordinate system like this, right? Wouldn't you think? Didn't say that explicitly, but if it doesn't say anything about the coordinate system, you have to probably think that's the intention. And so now the problem is we can't use the relative motion equation with vectors in two different coordinate systems. So let's just apply a rotation matrix. So to go from this coordinate system to this one, what rotation do we need? Yeah, 40. It's -40 because it's a clockwise rotation. So this is -40 degrees about z. So your rotation matrix is cosine of -40, sine of -40, 0, negative sine -40, cosine of negative 40, 0, 0, 0, 1. And now you just multiply that by the vector that we just got. So our velocity of A relative to the center of mass is equal to Q times this vector we got here, 6.3, 3.9, 0. If you have to punch all this stuff in element by element, it might not be worth it to do it this way. But if you have this programmed into your calculator, like the people in D-Form probably do, then this is a lot faster than doing the trigonometry to start with. Anybody have an answer for this? 2.31, 7.040. Okay, what's the alternative to doing it this way? The alternative to doing it this way is come up with unit vectors in these two directions. And then the R vector is 0.65 times the unit vector in that direction, plus 1.05 times the unit vector in that direction. Well, 0.65 times the unit vector in that direction. Anybody have any other questions about doing that, or you want me to go through that other approach?
You explained it once before. The rotation matrix in this context, we don't use the transpose at the end of it.
That's right. Okay, yeah. Well, think of it this way. Think of like what a rotation matrix is a thing that represents vectors in a different coordinate system. So first of all, think of it as like designed for vectors. Okay. And so that doesn't really explain the vector thing, but now I'm going to explain the tensor thing. So why do you need the transpose thing for the tensors in D-Form? Tensors are really, there's two types of vector information in tensors. There's the vector information that tells you how the faces are oriented. And then there's the vector information on each face telling you what the traction is. And so one of those rotation matrices you can think of as adjusting how the faces are oriented, and one of those affects the traction vector once you've adjusted those faces. Any other questions? Okay, so now, are we done? No. Actually, we're still on part A. But now we just use the relative motion equation. The acceleration of A relative to the ground is equal to 2.31, 7.04. Yeah, find velocity, thank you. Uh, 2.31, 7.04, plus what it says is the velocity of the center of mass, 5, -3. So 7.31, 4.040. The velocity of the point C, you do it the same way. But a key thing to realize here is like this is sort of a key part of understanding the motion of rigid bodies. Any translational quantity is different at different points on the body in general. So we're going to get a different velocity for the point C than we got for the point A. Angular quantities represent the entire body. So we'd still use the angular velocity that we were given Okay, but the new r vector, when we put it into the circular motion stuff, is going to tell us that the velocity at that point C is different than the velocity at the point A. But let's calculate the acceleration. So B is the same approach. Um, and then for C, we want to calculate the acceleration of the point B. The acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass plus the acceleration of the center of mass relative to the ground. And we have to think about it this way because there's no fixed point. But one of our assumptions is that the acceleration of the center of mass is 0. So this goes away. And all we have left is circular motion stuff. So the acceleration of the point B relative to the center of mass is alpha cross r plus omega cross quantity omega cross r, watermelon equation. And this is 0 because we're assuming that angular acceleration is 0. So come up with the r vector. We already have the omega vector and calculate it. And then you could use that in like what would be an engineering application of something like this? Well, if you had something with a certain mass at this point, you wanted it to stay fixed there, and you had to calculate how you needed to fix that mass at that point. You calculate the acceleration, figure out from the acceleration, use Newton's second law to calculate the net force that's applied, and then compare that to your method of fixing it on there. Any other questions about that one?
So the forces and the density and thickness, does that come into play in the watermelon equation at all, or once we're dealing with acceleration?
Yes. Yes. I take back. Actually, that's a super important point. Thank you. So all this stuff I said is not right. Okay, so the acceleration of the center of mass, I was thinking of kinematics. So like in kinematics, if you're not given the acceleration and the angular acceleration, then that's just implies that it's 0. In kinetics, if you're given forces and masses and stuff, then you can calculate those acceleration quantities. Okay, so that was a bad screw up. The acceleration of the center of mass and the angular acceleration, we're going to solve for these from the loads. Okay, so let's actually go through this then. That's that means that we're going to have to calculate this from Newton's second law. And we're going to have to calculate this from the moment equation. Okay, so this is a rigid body problem. So let's just go through the steps of a rigid body problem. So first, is there a fixed point? No. And so the about point is the center of mass. And now let's calculate the mass of the thing and the mass moment of inertia about the center of mass. The mass is the volume times the density. The volume is 2.1, was it? 2.1 times 1.3 times 0.1, 0.273 meters cubed. And so the mass is 0.273 times the density of 2,500. Okay, and then, so we have the mass and the mass moment of inertia about the center of mass is 1/12 times the mass times the length squared plus the width squared. And what do you get for that? Does Max have to do everything around here? Okay. 346.93 kilogram meters squared. That's step 3, free body diagram. You can think of that as step 3. Okay, well, basically we already drew this, but you can do it the way I did it before, or you can do it like this. The one thing you can't do is draw these in the opposite direction, write the negatives next to it. That's like a double negative, and that's going to confuse anybody who looks at what you're doing. And then at C, negative 400, 400, 300. And now step 4, I'm going to write out the table. Okay, so first at point A, the row vector, since our about point is the center of mass, that row vector is the vector from the center of mass to A. That happens to be the one we calculated already. Oh, no, we didn't in this new coordinate system. Well, okay, let's not get too clever about this. Let's just, so that vector is, the whole thing is tilted. How much is the thing tilted? Uh, that's right. Yep, we could do that. Um, cosine of negative 40, sine of negative 40, 0, negative sine of negative 40, cosine of negative 40, 0, 0, 0, 1, times negative 0.65 positive 1.050. What do you get for that?
Negative 1.17.
Okay. 0.39. Okay. Thank you. All right. So the row vector is negative 1.17, 0.390. The force vector is negative 200, negative 150, 0. And the cross product is 0, 0. What do you get for that cross product? $253.5. Okay, so now the other force is at the point C. Notice that C is just exactly across the origin from A. So that vector is just going to be the opposite signs. So the row vector is going to be 1.17, negative 0.390. The force vector is negative 400, positive 300. And the cross product is 0, 0. What is it? 195. Step 5 is Newton's second law. We don't always need to do that. Do we need to do it here? Yes. So if something doesn't have a fixed point, you need Newton's second law. So Newton's second law says negative 200, negative 150, plus negative 400, positive 300 is equal to the mass. What was that, 682.5? Times the acceleration of the center of mass. And so can someone tell me what the acceleration of the center of mass is? Say it again. Okay. Zero 0.22. And then 0 for Z. Any questions about that? And now the moment equation 253.5 plus 195 is equal to the mass moment of inertia about the center of mass, 346.93, times the angular acceleration. So what do you get for alpha? (1.3) positive, and then so if we're writing this as a vector, this is 0, 0, 1.3 radians per second squared. Okay, so now we have to go back to the relative motion equation. The acceleration of the point C is what we're trying to find. So the acceleration of C relative to the ground is equal to the acceleration of C relative to the center of mass plus the acceleration of the center of mass relative to the ground. This one is what we calculated from Newton's second law. This one is alpha cross R plus omega cross quantity omega cross R. So the acceleration of C relative to the center of mass at B. Okay, thank you. So that means we need to come up with a new R vector. Okay, so this is 0, 0, 1.3. The R vector is, let's do the rotation matrix thing again. So we have cosine of negative 40, sine of negative 40, 0, negative sine of negative 40, cosine of negative 40, 0, 0, 0, 1, times that point B, we're going to go 0.65 in the negative x and then 1.05 in the negative y. So negative 0.65, negative 1.05, 0. And can someone calculate that? Okay, and then this is the R vector. And then the omega vector was given 0, negative 0, 0, negative 6, crossed with the quantity 0, 0, negative 6, crossed with 0.18, negative 1.220. And can someone calculate that? Um, these are the kind of calculations you have to do to figure out like how long to fire like boosters on a, you know, on some kind of shuttle or something to make it get to this point at this place with the right orientation. And um, so I don't know, there's a lot of cool applications for this, but when you look at a problem like this and it looks like a pretty simple thing that you're trying to calculate, and then you see the number of steps that it takes, it's, what it really makes you think is like if you really had to do this in a real application with an object that had a more complicated shape than just a rectangular plate and with more forces and stuff, it sort of makes it clear that you would do it by writing a computer program and not do it by hoping that you made 1,000 hand calculations correctly, you know. But to write the computer program, you have to know how to make it work. Any questions about that? So, man, don't make the mistake I made. That was like, okay, so if you have a rigid body kinetics problem, so if you have a rigid body kinematics problem, first of all, okay, the accelerations have to be given to you. And so if no accelerations are there, then those accelerations aren't there. But in a rigid body kinetics problem, what we're doing now, those accelerations come from the loads. And you have to calculate those accelerations. Okay. Any other questions? Okay. Well, we have a test on Monday. And then after the test, here's the last things that I'm going to do for rigid bodies. So after exam 3, not after the exam. I mean, you can go after the exam, but in the next class after it, I'm going to do 3 cool calculations, in my opinion. Your mileage may vary. But the first one I'm going to do involves objects rolling down a ramp. And we're going to see if you line up a disc versus a ring versus a sphere on a ramp, which of those we can expect to like win a race to the bottom. You could maybe, you know, make money with this at a bar or something. Probably not. But the second thing, I think number 2 and 3 are the ones that you've probably asked yourself about before, but you haven't been able to calculate them up until now. The second one is all of our assumptions involving pulleys assume that there's no friction in the pulleys and the pulleys have no mass or size. That's obviously not realistic. So how do those things come into it? Friction comes into it in a very simple way. You just add a couple on to the, you know, that's equal to the friction. But dealing with the mass and size of a pulley is fairly complicated. We haven't been able to do it till now, but now we can. So we're going to compare a massless pulley to a pulley with a given mass and size. So I'll do a problem where you have a cable going over the pulley and 2 different masses, you know, and it's a pretty easy calculation to figure out without mass on the pulley how they're going to accelerate. then we'll add mass and choose a size for the pulley and see how that affects the acceleration. And then the third one is Pinewood Derby, which is just a chunk with a given mass that's resting on wheels with a given size and given mass. And we're going to see how all of these variables relate. We're not going to deal with air resistance, and we're not going to deal with rolling resistance or friction, although those are actually the easy things to add in. But we're going to deal with the relationship between how massive the body of the car is versus how massive and how big a diameter the wheels are, and we'll come up with an expression for that. Okay? All right. Have a good weekend. Yeah. Well, this actually won't help you in the Pinewood Derby itself because they make all the rules, like they basically tell you what to do. But we'll see the mathematical relationships, so.